Yes, doctor.
Yes.
Oh, okay. So we will start now with chapter 3, and you will see that you will find it very simple because once you know how to deal with forces and vectors, the equilibrium of a particle is very simple. Just you need to apply one equation. What is this equation? So when I say equilibrium of a particle,
Sum of
you will
forces equal to 0.
exactly you will think about the equation that sum of forces, of course, as vectors is equal to 0. Okay, so here, if you want, it's the application of a vectorial relation. In case you have a 2D application, it will give you two equations. In case you have a 3D application, it will give you three equations. Okay, so let us start to see what are the equations used in equilibrium of a particle. So to start with, a particle is in equilibrium provided that it is at rest or moving with constant velocity, because for both, the acceleration will be 0, and so sum of forces is 0. Okay? So to maintain equilibrium, we should satisfy Newton's first law of motion, stating that the resultant force acting on a particle should be equal to 0. And this vectorial relation can be written into, if you want, divided into components. In case we have a 2D application, it will give us two equations, sum of x equals 0, sum of y equals 0. So this is in 2D. And in case we have 3D application, you will add, so in 3D, you will add an additional equation, which is sum of fz is equal to 0. Okay? So as simple as that. Now, a very important step when we have the equilibrium of a particle is to draw the free body diagram of the object. What do we mean by the free body diagram? The free body diagram is a sketch showing all forces acting on the particle. Okay? So, because the equation you need is sum of forces equal to 0, you should determine all forces acting on your particle. They can be forces at distance, for example, the weight. Okay, the weight is considered a force at distance because it's the attraction of the Earth acting on the object, and it's between the center of the Earth, which is far from the center of the object. You can have contact forces. So for contact forces, you can have the normal reaction, for example. You can have a cable, a tension of a cable is a contact force, etc. Okay. Now, what are the steps to draw the free body diagram? So as we said, we should determine all forces acting on the particle. So we should imagine the particle to be isolated or cut from its surrounding. Okay. So in any problem, they will give you a figure. For example, a simple example, I have a certain inclined line. I have on it a box. A box is standing like this on it, and it's attached by a cable like this, let's say. Okay, I have a cable here, and the block is attached to it. So if I want to know all forces acting on the block, I should isolate the block. When I say I isolate the block, this means I will cut it from its surroundings. I will do this. If I want to take it alone, so I should cut it from its surrounding. Okay, and now when I do this, okay, I will have only the block. So I can just now take the block and think what are the forces acting on it. So first I say, since I did a cut here at the cable level, this means that the cable will do an action on my block, okay? So the first force I can represent is the tension of the cable. This is tension T. Now, since my block is in contact with the ground, okay, so I have the normal reaction. And also, if in case, I have two possibilities. I can have a smooth inclined surface. In this case, no friction. I can have a rough surface. Whenever you have a rough surface, Okay, you can have what is called the static friction. Okay, since my block is not moving, but still I can have a friction called static friction, which is applied on an object that is not moving. Okay, so let's say it's a rough surface, so I will also have a static friction. And now I have also the weight. Okay, the weight, of course. So this is the weight, and this is all forces acting on my system. So if I put their names, so this is W, this is the tension T, this is the friction F, and this is the normal reaction. Okay, now sometimes some of the forces are known. So for example, if the mass is given, the weight is known, so you directly put the value of the weight. So let's say it's a 2 kilogram block, so you directly put it's 20, so it's equal to 20 Newton. Okay, now in order to calculate the other forces, I should relate them. Okay, and we'll see in problems how we write sum of x equals 0, sum of y equals 0, and we solve for the problem. Okay, so now, so in step 2, I indicate on the sketch all forces that act on the particle, and these will include active forces, which will tend to set the particle in motion, and the reactive forces, like friction, for example. Okay, so the active force is any force that I am putting to try to move the object, okay, while the reactive force will tend to oppose motion. So here in the example I gave you, what is the active force? If I put a block on an inclined line, what will be the active force who will try to move the box?
Weight.
Weight, very good, because it will try to move down under the effect of its weight. And what are the reactive forces in the example I gave you that will try to oppose motion?
Friction.
Very good, friction, and also the tension in the cable, because also the cable is trying to prevent motion downward. Okay, so here in the problem, the tension and the friction are reactive forces. The weight is an active force, and the normal is neutral because it's not, it's acting perpendicular to motion. Okay, let us continue. Now, whenever I want to solve an equilibrium problem, I should be familiar with all types of special connections and reactions supports that I can have. Okay, so first, one of the most important connections is the spring. And of course, you are familiar with what is a spring and what is the expression of the force it can develop. Okay, so if you have a spring, in general, we deal with elastic springs, which means that I can write the force developed by the spring as K, which is the spring constant or called stiffness, and S, which is the deformation, okay, of the spring, which will be delta L, L final minus L0. So here, this expression is valid for both tension and compression, because if you have tension, what will happen is that L final will be higher than L0, okay? So here, you need to apply a force towards the right, okay? Now, if you want to compress, you should apply a negative force if you consider that this is the positive direction, okay? So if you want to compress your spring, you should do a force on it in the negative direction, and it will also be given by L final minus L0 times K. And now L final will be lower than L0. This is why the sign of F will be in the opposite direction. Okay? Now, what I want to tell you is that sometimes we have some springs that do not have constant stiffness. But in this case, we should give you K. Okay? So I can tell you, for example, I have a spring, non-elastic spring with K equal, for example, is function of S, 2S. Then the force will be okay, the force of the non-elastic spring okay, will be equal to 2s times s. Okay, so the relation is no more linear. Now, if they don't mention anything, if they give you just a spring and they don't tell you anything, then you can understand it's elastic. Okay, if it's not elastic, they should tell you in the given. Any question until here? So,
دكتور عندي سؤال.
yes.
انت يعني ان احنا بس نعمل small forces equal لزيرو نحسب الفريكشن
أكيد نحسب كل الفورس.
بس
Yes.
it's not in motion كيف بدنا نحسب
Even,
الفريكشن؟
yes, even. Look, we will see together that we have two types of friction. We have a friction called static, okay, and a friction called dynamic. You can have an object that is subjected to a resistance from the ground, but it's at rest. I will give you in detail this. We'll do this in example in detail, okay?
Okay.
Now, so before working with the free body diagrams, we should first consider the types of connections that are often encountered in particle equilibrium problems. First, we have seen together the spring, and now we will see cables and pulleys. You might find in several problems boxes attached with a system of cables and pulleys. So whenever you have this, you will consider that cables are assumed to have negligible weight and they cannot stretch. Okay, this is the difference between a cable and a spring. First, it cannot stretch, and second, keep in mind a cable can never sustain compression, because if you take a cable and you put it in your hands, try to do tension. If you push with your hands from the two sides like this, it will sustain tension, it will oppose motion. However, try to do compression on the cable. It cannot sustain compression. Okay, it will deform. It will give you this. This means that the cable cannot sustain compression forces, but it can sustain tension forces. Okay, so cables can support only a tension or pulling force which act in the direction of the cable. Now, concerning pulleys, pulleys are assumed to be frictionless, and thus any cable passing on a pulley will have a constant tension force. So if you see this, if you have a pulley and you have a cable like this from this side turning over the pulley and then going down, okay, since the pulley is frictionless, this means that if I do a cut anywhere in the cable, I will obtain the same tension. Okay, so the tension will not vary from one side of the pulley to the other, because I don't have any resistance here between any friction between the pulley and the cable that will reduce the tension force. Okay. Now, let us do a small example on how to practice in equilibrium of forces. So in this problem, we have the mass of the crate is 50 kilograms, and we want to find what is the horizontal force P needed to position the crate directly over the small car here. So you have a small car here, and the man is trying to push the box to put it just at its middle. So here you have a certain shift between the car, the middle of the car, and the middle of the box. What you are trying to do is to push point A in a way to have these two along the same line. Okay, so your objective here is to move a distance of 1 meter. Okay, so I should move it until here while keeping the same height. Okay, because this is possible because this red point is moving on the cable, so I can't change this length, this one. Okay, in a way to maintain a distance of 4 meters from the ceiling level. So what will happen is, at the final position, my cable will be here. Okay, and my box will be in this position like this. Okay, so since all forces of interest are acting on point A, so you can see that point A is the point of intersection of forces. If I want to represent the free body diagram, I will take point A as my system, and the forces acting on A, first I have the tension in the cable. Second, I have the action of the box, which is pulling it down through its weight. And third, I have the horizontal force of the man. Okay, so as you can see here, this is the representation of the free body diagram of A. Okay, now since I know the mass of the crate, I can deduce that the weight. Of course, here they use 9.81. In general, use 10 in exams. Okay, use G equal 10 because it will simplify calculations and the error will be very small. Okay, here sometimes they use 9.81. It's fine, so you will get close results if you use G equal 10. So for the weight, it's if you use G 9.81, you get 490.5 Newton, and in case you use G equal 10, you get 500 Newton. Now, I have two unknowns here. My two unknowns are the tension in the cable T and the pulling horizontal force of the man P. So since I have a 2D equilibrium problem, I can write two equations, sum of x equals 0 and sum of y equals to 0. So what I will do, I will take x and y axis like this. I will name this axis x and this is y. So this is x and this is y. And now all I have to do is to apply the equilibrium equations on x and y. Okay? Why they started by y? Because look, along y, you have only one unknown, which is the projection of t. While along x, you have two unknowns, which is the projection of p and the projection of t. So here it's easier to start with sum of y. Anyway, if you started with sum of x, it's not wrong. You will get a system. So you need to solve for the second equation before going to sum of x. Okay? So let us start first by sum of y equals 0. Along y, what do I have? I have, of course, the weight. So it's minus w. And I have the projection of t. The projection of t is positive. It's upward. So plus t. And I can see from the figure that I need this angle. So it's plus t sine of theta. Okay? So to be able to do my projection, I need to find angle theta. How to find angle theta? It's very simple. If you look at this figure, they gave us an information. Okay? They gave us, we have, this is 1 meter and this is 4 meters. So we can say that for angle theta, we can write that tangent of theta is equal to 4 over 1. Okay? And this will allow us to calculate the angle theta, which will be 75.52 degrees. So now we can do along y, it's t sine theta minus w equal to 0. We can get that t. So from the first equation, we got our first unknown, which is t. Now we can move to projection along x. So if I do projection along x direction, what do I have? I have tx minus p equal to 0. And what is tx? If I do the projection on x-axis, okay, the projection of t on x is simply t cosine theta. So t cosine theta minus p equals to 0. I already found t from the previous equation. All I have to do is to replace t by its value. And now I can get my second unknown, which is p. So by this way, I solve for my two unknowns, t and p. Okay? Here it was easy because t is present p is only present in sum of x. So to get t, you can just do sum of y. Sometimes, if p was like this, for example, then you will have t and p in both equations, but it's fine. You will get two equations with two unknowns, so you can solve a system in this case. Okay. Any question on this?
All good.
You find that I am moving fast. If you find that I am moving fast, I can slow a little bit. So it's fine for you like this?
Yes.
Okay. So we continue next time. And if you have any question, you can send me a message whenever you want. See you next time.
Thank you.
Bye bye.